This is one of the cases that never happened.
From files that don't even exist.
At the dawn of the 19th century, Europe stood on the edge of immense change. Steel steam engines roared inside vast factories, while iron railways cut across the land, linking cities as if by invisible threads. In the streets of Paris and Vienna, towering wrought iron cranes lifted heavy metal plates that would become boilers, ships, and the machinery of a new age. Humanity seemed determined to conquer the world with steam and iron. Yet within that great industrial surge, fate left a small, almost invisible crack in the fabric of progress. In our imagination, that crack became something extraordinary. A layered mechanical miracle, the first three-dimensional printer in history. The story begins in Vienna, in a small workshop where a young Swiss craftsman named Yóhann Kírchhof worked. His family had made clocks for generations, delicate mechanisms in which every gear tooth and every spring demanded absolute precision. As a boy, Kírchhof would spend hours bent over a microscope, watching tiny grains of metal powder settle into fine glass molds as master clockmakers formed intricate patterns on their dials. One evening, when a steam engine from a nearby factory was brought into the workshop, Yóhann noticed something unusual. A burst of steam struck a heated speck of metal powder and fused it instantly into a solid sheet. In that moment, an idea took shape. If powdered material could be guided by a controlled flow instead of a human hand, then perhaps any object could be built layer by layer without the need for expensive casting molds. Kírchhof spent years experimenting. He studied ceramics brushed onto clay sheets, devoured books on the emerging science of metallurgy, and filled notebooks with sketches and observations. By the year 1807, at the age of 30, he had assembled what he believed to be the world's first additive machine. It was crude, but brilliant. A large steam boiler forced fine metal powder under pressure through narrow nozzles into a sealed chamber. Inside, a moving platform advanced slowly as thin layers of heated material were deposited one atop another. The steam helped each layer harden almost instantly. The first object Kírchhof produced was a gear with 32 teeth, printed entirely without a traditional mold. When he showed it to a colleague, the man could hardly believe what he was seeing. The teeth were perfectly symmetrical, and the surface was so smooth that it reflected candlelight like a mirror. A little-known archival note from 1811, written by the French engineer Dupont, mentions the possibility of layered pages for the creation of complex forms, an idea that seems to refer directly to Kírchhof's experiment. News of the invention began to spread across Europe. Small factories in Vienna and Berlin started ordering printed components from him: toothed belts, milling tools, glazed ceramic handles. Each commission was carefully recorded in a growing journal: measurements, powder compositions, steam pressure, and results. Other engineers soon took interest in this layered method of fabrication. In several workshops, the first printed blanks began to appear, unfinished forms later refined by traditional means, yet created without costly molds. Within just a few years, the technology began to evolve. Early electric machines, large and awkward though they were, gradually became more reliable. In Vienna, engineers tested new materials: copper, bronze alloys, clays, and even obsidian-based ceramics. New mixtures reinforced with cellulose fibers allowed them to print flexible sheets, which were soon used in attempts to create lighter parts for steam engines. In 1813, the first small additive factory opened in Prague under the name Adelshof. It housed 3 such machines and produced dozens of components a day, constantly refining new shapes that reduced the weight of steam-driven wheel assemblies. This marked the beginning of a profound transformation. Craft was turning into a new form of industry. Traditional blacksmiths, who had long depended on forging each piece individually, began to lose some of their work. At the same time, an entirely new profession appeared: the printer designer. Young people trained in technical schools learned to prepare punched design cards before the machine was even started. Instead of spending weeks making a mold, they could simply cut a pattern into a card, load the machine, and begin production. At the École Polytechnique, founded in 1794, early educational programs began to include additive methods, and by the 1820s, students were already printing small components in laboratory settings. By the 1820s, Europe had several specialized manufacturers of additive machines, with supply networks stretching across much of the continent. In Russia, an experimental plant appeared in St. Petersburg in 1825 under the name Moscow Metallic. There, engineers developed large printed parts for railroad systems using translucent alloys of copper and tin designed to reduce metal fatigue. Additive methods allowed them to create rails with internal lubrication channels, doubling their lifespan compared with conventional forged rails. As a result, railway lines became more reliable, and economic growth accelerated in new ways. By the 1830s, the idea of modular production had emerged. Large factories broke their products down into smaller sections, each printed in separate workshops and then assembled in a central plant. One notable example was Rohrenwerk in Vienna, where steam pipelines were manufactured. Instead of casting enormous solid blocks, the company printed separate ceramic-coated alloy sections that could be joined quickly using a kind of steam-based adhesive. Production delays that once lasted weeks were reduced to just a few days, doubling the company's output. Before long, similar methods were adopted in England, where steam-powered industry was expanding rapidly. In 1835, London hosted the first public exhibition of this new technology, called Printed Wonders. The gallery displayed hundreds of objects produced entirely through additive means: delicate jewelry with microscopic ornamentation, intricate gears, and forms too complex for ordinary casting. Visitors were astonished, describing the machines as miracle mechanics. Governments took notice as well, and soon began funding research into additive manufacturing, worried that rival nations might gain an advantage. Then came another leap forward. In the 1840s, engineers in Berlin developed an electric microcontroller capable of regulating the flow of powder with far greater precision than any steam-driven pump. This paved the way for electric printers, which by the 1850s had replaced steam-based systems in many modular factories. The new machines were half the size and consumed only a third of the power. That meant they could fit not only in industrial workshops, but in small businesses and even homes. By 1854, the city of Saratov already had several tabletop domestic printers, compact mechanical devices capable of producing tiny wooden parts and wax models. Sold through industrial catalogs, they became the earliest form of mass access to additive production. With electricity came new approaches to education. Schools in Prussia began teaching the fundamentals of additive technology. Thanks to affordable tabletop printers, students could make small mechanical models, gear teeth, simple devices, and even miniature organs for biology lessons. By the 1860s, school books included illustrations designed specifically for students to reproduce on classroom machines. By the 1870s, Europe had developed something resembling an early marketplace for design files. Craftsmen could prepare a design as a punched card and send it across the continent to another workshop, where the object would be printed in metal or ceramic and then returned. In spirit, it resembled a modern online marketplace, only without the internet. The first model patents appeared, and legal scholars began drafting laws to protect what we might now call digital intellectual property, since anyone could copy a design from a book and print it in their own shop. Among these developments, one moment stood out in particular. In 1885, a Swedish engineer named Lars Vigren, working in Stockholm, adapted the principle of the electric arc from a later patent concept and created the first form of alloy print welding. This made it possible to fuse printed parts together without separate fasteners, allowing for seamless, unified structures. The discovery transformed the production of heavy industrial machines and enabled lighter, stronger steamships and railway bridges. By the early 20th century, the world looked very different from the one we know. In Paris, engineers were already building early aircraft prototypes with wings printed from lightweight aluminum alloys. Thanks to those materials, airplanes reached heights that, in our real history, would not be achieved until decades later. In Germany and America, mass production based on layered printing cut the cost of automobiles in half by the 1910s. Many households had their own domestic printers, capable of making replacement parts for everyday objects, from ceramic teapots to small brass locks. Printers became so common that in 1915, a London magazine called Home Craftsman began publishing evening projects and printable household designs. The cultural impact was just as dramatic. Artists used additive methods to create sculptures with hidden internal spaces impossible to carve by hand. At the Venice Biennale of 1889, visitors saw a vast installation made from hundreds of printed ceramic forms assembled into a giant three-dimensional mosaic. Philosophers debated a new question of creation. What does it mean to create when anyone can reproduce anything? Writers, meanwhile, embraced the romance of the machines. Their novels filled with inventors who could build entire mechanical orchestras in a matter of days, printing each part from lightweight alloy. And all of it began with one simple moment: a young clockmaker watching steam fuse a grain of metal into a solid layer. From that moment, an ordinary speck of powder became a kind of digital material, capable of becoming any shape the mind could imagine. Over the course of a century, that idea grew from a small Viennese workshop into a network of vast factories, from simple gears to aircraft in the skies over London, and even to the earliest attempts to print biological tissues in laboratories during the 1880s. In this alternate world, three-dimensional printing arrived at the very start of the Industrial Revolution. As a result, society became more flexible, more responsive to change, and far more democratic in its access to manufacturing. It was a world in which the phrase, "print whatever you want," sounded as natural as "download an app" does today. And when we look back from our own digital age and ask what might have happened if such a machine had appeared 100 years earlier, it is hard not to feel a shiver at the thought. Human society might have changed beyond recognition if, already in the 1800s, people had been able to turn thought directly into material form. That is where this alternative history begins, in a world where reality itself is built in layers, and history moves not through cast iron, but through waves of metallic dust shaped by imagination. In that world, everything that seems impossible to us today would have been only another tool in the hands of young Yóhann, who in 1807 first took a grain of metal and made it dance to the rhythm of steam.